Now, since gold had been reported to have the biggest spin Hall effects, we figured, oh, this is a nice material to see what we get. So we made gold wires like this. So if you zoom in, looks very nice. These are gold wires about 100 nanometers wide, a little more, 110. They're 60 nanometers thick, and they have different spacings. And then what we can do is we can pass a current through here, measure voltage there, and then change it around, we'll put a current through here, measure voltage there, so have different distances to see how the signal decays. And so, again, this is kind of the measurement that we do, pass a current through here and measure voltage there. So for the average electrical engineer, that seems like an odd measurement to do, especially if there's nothing magnetic, right? But what we saw was kind of surprising. So here is the voltage normalized by this current, so we call it a non-local resistance, as a function of temperature. At high temperature, it's positive, and then it becomes 0 around 80 Kelvin, it becomes negative and flattens out here. And that looks very curious. And we thought, oh, there must be something interesting. And so the first thing that you have to notice is when you pass a current through here, the current doesn't go like I'm indicating here with this arrow. I mean, it's a diffusive current. It actually spreads out where you have this type of. And from this diffusive current alone, you can already get a voltage, because some of the current has a component here in this crossbar that goes along this direction. And you can calculate very easily how big this current should be. It should just be given by the resistivity of the material, and otherwise a geometric factor. So L is this distance, W is this width, T is the thickness of the film. Now, we can measure the resistivity of our wires very well, so we've done that. And when we plug in that resistivity and the geometric numbers that we know, we get this blue curve. So at high temperatures, our signal is dominated by this diffusive contribution, but at low temperatures, there's an additional negative contribution. It's like, oh, maybe this is are the spin currents that we're looking for. Well, there's a problem with that, because you can also calculate very easily what you expect for the spin currents. Essentially, you know if you take a current here and convert it to spin current, that's due to the spin Hall angle, then you know how the spin current decays here. It decays with the spin diffusion length. And then here it gets converted back into a spin current, charge current, and it's again the spin Hall angle. So you have the spin Hall angle squared, you have this decay with the spin diffusion length, and then you have some other, the resistivity and some other geometric factors here. The biggest problem with this is